Hey people! So today we're going to look at calorimetry. Well, this is a method of figuring out in a reaction, or just as simple as dissolving something, how much heat does it give off? Or how much heat does it absorb? To do that, you need a little device, and that device is called a calorimeter. Sounds like a sophisticated device, doesn't it? No, it's not. You're going to build one yourself. All you need to do is 2 styrofoam cup. So let me draw that for you. So you're going to take a styrofoam cup, okay, like this. And I like to double it to give it a double protection. That sounds cheesy, but a double insulation. Okay, there you go. Now, the question is, why styrofoam cup? Can I do paper cup? Yeah, certainly. Styrofoam was a little bit better. Okay, paper will work too. Now, the thing is this. You need to make sure that the cup that you're using is an insulating material. Okay, insulating material, not a conducting material. So you'll never use a metal cup. Okay, that's why you don't use metal cups. Very rarely when people use metal cups. When people use metal cups, I don't know why they would use metal cups. Okay, now why would they use styrofoam cups? It's because it's insulating. The fact that it is insulating, that you don't give off heat that much. You insulate your heat within. Okay? Nor is it easy for heat to get in. You know what I mean. Okay? It's insulating in a way that the styrofoam doesn't get heat up that easily. At the same time, it does not release heat easily. Because if you think about it, if this cup was made out of a conductor, okay, and you have a reaction that is exothermic. We heard about exothermic the other day. This is the reaction where your enthalpy is it's lower. What am I saying? It's lower in the system than before the reaction. So before the reaction, you have a certain enthalpy. But after the reaction, the enthalpy dropped. So delta H is a negative number. Where did the energy go? The energy went to the surroundings. So when you use an insulating cup like styrofoam, okay, the styrofoam might absorb some of the heat. I shouldn't say might, it will, but very little of it. Even though if it absorbs some of the heat sort of kind of stay here a lot longer before it gets driven off. Because that's what insulating material does. Okay? However, if this was a metal cup and you have an exothermic reaction happening here, the heat will very quickly get absorbed by the metal, and it really quickly gets out of the metal. So the metal absorbs heat very quickly and releases the heat to the surrounding very quickly too. That's why when you're heating metal, you'll notice that the metal will get hot very, very fast. Okay? But again, it's also very fast when you cool it down. All you have to do is let it sit in the air and it will actually cool down pretty quickly. You don't want that. Okay, you don't want your calorimeter to be made out of something that can heat up fast and releases heat fast, because your data is going to be very fast in a way that you may not be able to see the temperature change. Whereas if you have an insulating material like styrofoam, okay, the heat will stay here and drive the thermometer up or down depending on the type of reaction. So, hey, to double the protection, we put 2 insulating cup. On top of that, we add a lid on top. On top of that, we stick in a thermometer, and we also add a stir stick. Now I see some student, and what they do does not really impress me, is that they use the thermometer as their stir stick. Try not to do that. I mean, it works. Of course it works. But you don't want to do that. Okay? You don't want to break your thermometer. You can't break your stir stick. Okay? Now, what goes inside the calorimeter is your chemicals. Okay? Depending on what you're doing, the reaction, of course, is in here, which is where the system is. Okay? You could be dissolving a solute with water. You could be doing a neutralization reaction like we saw previous class. Okay? Or you can even be adding solute to a certain solution by making certain assumption. Okay? Whatever it is. Okay? It's happening inside this calorimeter. Okay? To do this, you need to take data. And there's really only two pieces of data that you need. One is, what is the initial temperature before the reaction? Two, what's the final temperature after the reaction? Let me say that again. There's only two data that you really need to take. What's the temperature before the reaction? And the temperature after the reaction. And the reason for this is that these two pieces of information will allow you to calculate heat, which is, of course, Q. Because Q is equal to mc delta T. That's a very important equation. M is mass, measured in grams. Okay? Usually, it is the mass of the solvent. Okay? Usually it's the mass of the solvent. If you're dissolving a solute here, it is the mass of the water that gets put in here. Why? Because that's exactly what you're measuring. C is known as heat capacity. And that is measured in joules per gram degree Celsius. Now, heat capacity is indicating how much heat does it require to raise this temperature 1 degree when you have 1 gram of solute put in. Or 1 gram of water, 1 gram of water, or 1 gram of whatever this is. Let me say that again. How much heat does it need to raise 1 gram of this by 1 degree Celsius? Let me write that down. Let's write that down together. Heat required to raise the temperature of 1 gram of substance or 1 gram of your solution by 1 degree Celsius. Okay? Now, if you're using a solvent that can easily heat up, so things that heats up quickly will have a low C. Okay? Whereas things that heats up slowly will have a high C. Now, what is an example of a high C? No, I'm not talking about no orange juice. I'm talking about water, and that has a heat capacity of 4.18 joules per gram degree Celsius. That's actually pretty high. So So when you're heating water versus heating something else, water takes a longer time to heat. However, water also retains its heat longer than some of the other solvents out there. Okay? And that's true, something you do know already through previous topics. Water is highly polar. It forms so many hydrogen bonds. When you're heating things, what you have to do is you're breaking those hydrogen bonds. If there's lots of hydrogen bonds to break, you're going to need more energy, right? So it makes sense, of course, that water has a high heat capacity. You want to raise 1 gram of water by 1 degree? Add more heat. In this case, they already figured out C for you, which is the heat capacity of water, to be 4.18. Okay? If you're looking at stuff like alcohol, that will be lower. That will have a lower heat capacity. Heats up quickly, but also cools down quickly. Okay? Now, remember what I mentioned. When you're doing calorimetry, there's only 2 pieces of data that you need: before temperature and after temperature. Hence, delta T. Delta means the change of. So you're looking at, of course, final temperature. Final temp. Okay, and of course, initial temp. And you're looking at, of course, the difference between the two. Okay, and of course, we're looking at degrees Celsius. Why would we be working at degree Fahrenheit? Okay, so that is your calorimeter. Hopefully we have the opportunity to build one of these. I mean, it's pretty cheap if you think about it. There are, of course, other calorimeter where it's a little bit more expensive. Of course, they're made with a much better insulating material. Okay. So, again, something that we need to keep in mind. Now, another thing, of course, is that what we learned last time is a couple of values. Let's say we're doing this right here. Okay, and what's in here, let me just mark that down. Okay, what's in here, let's say, is a neutralization reaction. It's actually HCl plus NaOH. Okay, we're doing neutralization reaction here. And I would note the fact that this reaction is exothermic. How I know? Well, the final temperature is higher than the initial temperature, meaning that this system is exothermic because it gives off heat. Right? And if I was doing this under standard condition, I will probably have figured out using this equation right here that delta H is equal to negative 57.3 kilojoules per every mole of whatever's limited. Could be HCl, could be NaOH. Okay? Now, let me just reiterate this a little bit. Okay? If this material right here is very good at insulating what's going on in here, the number that you're going to get is going to be very close to this. But I can tell you right now that under no circumstances in your lab at Milliken Mills High School, whatever high school, even in university, you're not going to get this number. You'll get close, but you'll never hit this number. Why? Because number one, we are working in an open system where heat have the ability to transfer even mass from the system to the surrounding. There's a transfer there, so there'll be interference. Number two, your insulator, even though it's very good in terms of retaining heat and not let it escape too easily, is still not perfect. Your calorimeter will take away some of the heat. it will absorb some of the heat. This styrofoam cup right here will have the ability to take away some Q. When that happens, guess what? You're not gonna get this number. Okay, that number is gonna be a little lower or higher, depending on the reaction, right? Because of that, how is delta H brought about? Well, to make things a little easier to understand, is that delta H is equal to plus or minus the absolute value of Q. Okay, over N. Okay, obviously this is the amount of solute that you have to keep in mind, which we will see later on exactly how that works. And it's pretty simple. It's really nothing extraordinary. Okay. But let's cross this out for a sec. Okay. That is really just to get delta H to be kilojoules per mole. But if you just want kilojoules for the sake of kilojoules, is really just the positive or negative absolute value of Q. And it is going to be positive if if endo. It is going to be negative if exo. Whatever your equation will get it to be, you make sure that is an absolute value. So that's another important aspect about the experiment that you guys are required to do. All right, let's erase some of these things. Let's draw this back and have that back together. I like my stir stick. And the solution back in here. So let's take a look at some questions that we can think about. Okay, so question number 1. Let me just erase. Oh, this is not required. Okay, so let's do some thermal chemistry question based on MC delta T. Okay, so here it is. Example 1. I have 7.46 grams of potassium chloride. Okay, and I dissolve this in 100 milliliter of water. Okay, so 7.46 grams of potassium chloride dissolved in 100 milliliters of water. So picture that. And the initial temperature, I would say TI, was 24.1 degrees Celsius. And the final temperature, which I call TF, is equal to 20 degrees Celsius. Okay, I want to calculate the amount of heat being transferred. That's a very lovely question. I would call this an A type of question. Dissolving solute type of question. Okay, I will do 3 types of questions, and this is actually the first one. So let's take a look at what's going on here. Okay, since I still have my calorimeter here. So I'm going to drop 7.46 grams of KCl. And I'm going to put in 100 milliliters of water. And I'm going to use my stir stick to dissolve this. Now, before I do that, I take the initial temperature. So basically, I take the initial temperature of water. I'm going to put the water first. Okay, I'm going to put the 100 milliliters of water first. And I notice that the temperature is, 24.1 degrees Celsius. That's my initial temperature. Then I'm going to add KCl in there, 7.46 grams of it. Then I use my stir stick and stir. And I notice that my thermometer will change. In fact, the temperature dropped. Now, when do you stop? You usually stop whenever it stopped moving. You'll notice that your gauge right here will drop to 20. Make sure you mark that down, because afterwards it may actually rise. When it starts rising, you know for a fact that, reaction has complete. The lowest that I got was 20 degrees. Wow, so I went from 24.1 to 20. So wow, temperature decreased. Okay, now we'll worry about that later because that will be part of my part B question. I want to know, what is Q? What is the heat being transferred? So let's do that. Q is equal to mc delta T. Now, remember, M is not the mass of the solute. No. It is not the mass of the solute. It's actually the mass of water, because what's being raised in temperature here is water. You're not raising the temperature of KCl. Come on, give me a break. You're raising the temperature of water because you dropped the KCl. So what's the mass of water? Now, you know that the volume of water is 100 milliliters. The density of water is a gram per milliliter, meaning that for every milliliters of water, that's equivalent to 1 gram. That's what density means. So 100 milliliters means 100 grams. Well, you're looking at water, so the heat capacity of liquid water is 4.18 joules per gram degree Celsius. And the difference in temperature is 20. Well, it really doesn't matter which one you go first, actually, because it's going to be an absolute value later on. Remember that. It's 24.1 minus 20. I want to keep it as a positive number because, as I said, it really doesn't matter. Degrees Celsius. Now, hey, crossing out units, grams and grams cancel. Degrees Celsius cancel, and you're left with joules, which is, hey, it is a unit of energy. And the answer here is 1,713.8 joules. Okay? Now, what will be the delta H in this case? Delta H is dependent. Remember what we said. Delta H is the positive or negative absolute value of Q. We found Q. Q is 1,713.8 joules. So what is delta H? Well, it's really the same number. You just have to put a sign in front of it. What's the sign? The sign is going to be positive. Why is it positive? Because the reaction is an endothermic reaction. That's why it's positive. Okay? So the answer, the heat transfer, okay, make sure you get the language right. The amount of heat transfer is 1,713.8 joules. The enthalpy, the change in enthalpy, not the enthalpy, but the change in enthalpy is positive of the same number. Now, let's do part B of this question. The part B says, calculate what we call the molar enthalpy of this solution. Now, when they say molar enthalpy, obviously mole has to be involved, right? Okay, and molar enthalpy is usually joules per mole. Molar enthalpy, so let me say that one more time. Molar enthalpy is usually joules per mole. Mole, where's the mole coming from? Mole is the number of solute that you put in. So let's do that right here. Okay, mole is equal to 7.46 grams, because that's how much you put in. And if you were to turn that into moles, you would divide that by the molar mass. That is 0.1 mole of KCl. So the molar enthalpy, in this case, of this solution right here, so delta H sol, because it's a solution, is equal to your delta H divided by N, which is equal to positive 1713.8 divided by 0.1 mole. So your answer is 17,000 joules per mole. Since this is such a big number, this is really 17 kilojoules per mole. Because in your CRC handbook or your IB data booklet, it is usually given in kilojoules per mole. So this is the first type of question where you're dissolving a solute. So let me go back and take a look. Okay, because this is something that you are going to do for real, because I will give you some KCl, okay, and you will have to weigh it. I'm going to give you some water, and you're going to have to look at the volume. So you put some water in here, okay, find the initial temperature, drop some salt in there, mix the two, wait until the temperature stops fluctuating, and find the final temperature. Okay, with that information, which is the amount of water, you use water, so that's 4.18, and the difference in temperature, you can find the amount of heat that got transferred. Knowing that this is endothermic, your enthalpy will be a positive number. If I were asked, hey, what is the molar enthalpy, which is what you guys are usually going to be giving me, because it involved with how much mole of solute you use, you would divide the enthalpy by the number of moles of solute like we did right there. Okay? Very standard question. And for sure, I'm going to tell you right now that one of the things that we're going to do is that I'm going to give you a whole bunch of different solutes. And you are going to do this experiment. And you're going to rank these solutes according to which one has the highest molar enthalpy to the least molar enthalpy. Sounds fun, isn't it? Okay, or group them. Which one of these solutes are exothermic, gives off heat, and which one of these solutes captures heat, endothermic. Hopefully this question sort of answer a lot of those questions right now, because hey, it only makes sense if you're actually doing these things, and you will be. All right, let's take a look at the second type of question. The second type of question, which is also it's the same thing. Dissolving solute, but you're not dissolving solute in water this time. You're dissolving solute in a solution. Okay. Let's take a look at how this works. But I got to tell you this right now. You're dissolving solute in a solution. In this solution, the solvent is still water. It's just that unlike this example where you're actually using water, no, you're using something that has moles in it, but water nonetheless. What that means is that you're still using 4.18. However, that because it's not really just water that is being heated up, your answer is not going to be very deadly accurate. Deadly accurate. But it's good enough. However, it actually gets worse and worse and worse if the solution that you're using is more and more and more concentrated. So being diluted makes better sense if you're going to use 4.18. Because if you don't, you might need to find the density of your solvent, whatever that solution is. And then the math becomes harder, I guess. All right, let's clear this up. Okay, and let's take a look at my second example. So question type B. In this case, you're adding solutes to a solution and not just water. And here's an example. Let me just draw out this example for you. It's going to be copper sulfate. That is the solvent. Okay? And you're going to add sodium to it. Now, this is going to be a single displacement reaction. Let me just kind of draw that for you, plus Cu. But whatever it is, it really doesn't matter. It is really only matters for the balancing purposes. Okay? So let's say in this solution, you are working with 0.5 molar at 100 milliliter. And you're going to drop 6 grams of sodium in there. Okay? The difference in temperature that you're going to get by doing this is 20 degrees Celsius. And heat was actually released. Automatically, you should think, oh, this reaction causes heat to release. That must be exothermic. And the difference in temperature is 20 degrees Celsius. That's cool. That's cool. Okay. So let me show you exactly what's happening here in this diagram. So you have this in there already. Okay. And the concentration and volume of it is this respectively. Then you take 6 grams of sodium and you drop that in there. And you mix, and you'll notice that the difference in temperature is 20 degrees Celsius, and this thing got hot. Really hot, actually. And I want to know what is delta H of solution for this reaction. Okay, so that's what we're going to do. So first, let's calculate delta H. Well, in order to find delta H, first we have to find Q. Okay, so Q is equal to mc delta T. Well, it's written all over, okay? That the mass right here is going to be the mass of the solvent. In this case, it's going to be copper sulfate because this is what's dissolving the sodium. So that will be 100. Now you may be thinking, wait a minute. I know water is 1 grams per milliliter. So 100 milliliters will be 100 grams. But this is not water, is it? This is a solution of sodium of copper 2 sulfate. Well, I mean, you did use water to make copper 2 sulfate. So a lot of this solution is pretty much water-based, right? So we are going to assume that there's enough water here to maybe have the same density. Now, that is one assumption, obviously, you can make. And we are going to pretend, or use the fact that 100 milliliters of copper sulfate solution is kind of like a 100 gram. Okay, so not just that, okay, C will also be the heat capacity of water. Okay, that's, not entirely correct, but it's close enough. All right, let's continue. So delta T is said to be 20 degrees Celsius. That is actually being told that. And when you multiply the 3 number, you're going to get 8,360 joules. Now, what will the delta H be? Delta H will be 8,360 joules. By looking at the question itself, it says right here that heat was released. This is a big one because this is an indication that this number is a negative number. So it's a release of 8,360 joules of energy. Now, let's take a look at the next part. Okay, now that we found Q, we need to find out what is the molar enthalpy of this stuff. Now, to do that, we're going to have to use a little bit of stoichiometry right there. So let's kind of put this aside right here. Let's put this aside, that delta H is equal to negative 8,360 joules. Okay, let's erase all of this because I need some room here. Okay, I need some room here. So my answer needs to be in joules per mole. Okay, we're not going to do what we did before. Before, we kind of took the solute. Okay, we kind of took the solute, changed that into moles, and then divide this by that mole. But no, we're not going to do that because we're unsure exactly which one here is limited. Which one is the one that dictates the reaction to proceed forward, right? Hey, I guess what you need to do now is to see, hey, who's limited here? So let's do the math. Let's do some grade 11 math. So 0.5 moles per liter of copper sulfate, and you have 0.1 liters of it. Liters cancel. Well, what we do know from balancing the reaction is that for every mole of copper sulfate is equivalent to 2 moles of sodium. Moles cancel, copper sulfate cancel, and for every mole of sodium, you're looking at 23 grams. Here you go. So by doing the stoichiometry, you get 2.3 grams. Now, let's do a little review in terms of what that means. That means with this amount of copper sulfate, you need at least 2.3 grams of sodium for the reaction to go to completion. Let me say it again. With this amount of copper sulfate, you need at least 2.3 grams of sodium for this reaction to go to completion. Well, let's take a look. Are you given more or less than 2.3? Oh, you're given 6? Yikes. That means sodium is in excess because you really only need 2.3. You're given 6 here. That's too much. That's excess. If that's excess, that means copper to sulfate is limited. And guess what? You are going to use the limited reagent to determine what delta H is. Right? Now, you want to find the mole of this. So that's 0.5 moles per liter times 0.1. Okay? So that's 0.05 moles. So 0.05 mole is what drives this reaction forward. It is the one that you will use to determine the molar enthalpy for this question. Okay, so delta H of solution is equal to the delta H over the mole of the limited reagent, which is of course negative 8,360 joules. Divide that by 0.05 mole. So yep, you have here your moles per liter. So that will be 167,200 joules per mole. Don't forget, it's a negative value. Okay. Hopefully this is not a problem for you, but that's what you have to do if you're adding solute to a solution inside a calorimeter. I have one more example for you. So let's take a look at the last example and then we'll call it. So let's wipe this clean. And let's take a look at the third example. All right. C-type. Okay. You're looking at delta H of neutralization reaction. Usually just write N. Okay. So here it is. You have hydrochloric acid reacting with sodium hydroxide. That will give you water and sodium chloride. So what you did here is that you put some HCl here, you put some NaOH here, and you let the reaction go. Okay, of course, okay, before you do any mixing for this type of reaction, you have to make sure that when you put one of the participant in there, you put HCl in there, and you take the temperature. And then when you put the NaOH in there and mix, you take the final temperature, and you'll notice that the final temperature here, or the change in temperature here, is 7.6 degrees Celsius. And we all know that in neutralization reaction, it is always exothermic. Keep that in mind, okay? So your final temperature is going to be a higher number than your initial temperature. Let's put in some numbers. Let's take a look at what we put in. Let's say we put in 0.5 moles per liter here. Okay, and you have 0.025 liters. Okay, and you have 0.8 molar here. Same idea. Okay, now this is the trick here. This is the cool stuff. Let's say this was the reaction that you're doing. Okay? And let's just say the volume right here is not given. But you're to find out what it is. This is sort of like a titration question, doesn't it? It is. It's sort of like a titration question, but you're not looking for concentration here. No, concentrations are given. What you are looking for is the volume of NaOH, which will cause this reaction to proceed without anyone being in excess. You get what I mean? You're trying to find what the volume of NaOH be for it to have no excess, where the mole of HCl is equivalent to the mole of NaOH. Okay. Now, to do that, it's pretty simple. It's really just a stoichiometry problem. Okay. But in this case, what I do want to find out is what is the delta Hn for this question. Okay. But of course, the first thing that you need to know how to do, of course, is to find out what that volume is. But it really doesn't matter. It really doesn't matter because we're kind of setting whatever this. Actually, it does matter. Okay, you actually do have to know what the volume is because we need to find out M in this case. Okay, so let's do that. Let's find out exactly what's the volume of NaOH. So we have 0.5 moles per liter of HCl, and we have 0.025 liters of it. Okay, so now you have moles of HCl. We know that for every mole of HCl, it's equivalent to a mole of NaOH. Okay, that's good enough. All we need, of course, is how much mole of NaOH, and that will be 0.0125 mole of NaOH. Now we have enough information to find volume, because volume is just mole over concentration. Okay, so that will be 0.0125 mole over the concentration, of course, is being 0.8 moles per liter. Hey, we found it. Okay, the equivalent volume for the 2 moles here to equal is 0.0156 liters. Now, this is very important. This is actually quite important, because right now you're trying to find delta H, which means you need to find Q first. Q is equal to MC delta T. What is M? That's the question. What is the mass here? Now remember, these guys are solution. Just like the previous example, we can pretend that the solution is mainly water. So we can use the density of water to abbreviate what the mass of the 2 solvent is going to be. In this case, there's no such thing as solute or solvent. It's just mixing 2 solutions together. So mass in this case is going to be 0.025 liters, which is really just 0.025 grams, plus 0.0156 grams, which we calculated because we want to make sure that the mole of this and mole of this is the same for the reaction to go completion without any of these guys being in excess. So that's your M, the total volume, which is total mass, times 4.18 times the change in temperature, which is said to be 7.6, and it's going to be exothermic. Okay, all that hopefully will give you negative 1,290 joules. The reason why I said negative is because this is exothermic. This is the delta H value. Okay, so you can say right here that at end point, which is what this really is, okay, mole of HCl equal to the mole of NaOH. So does it really matter which mole you're going to use to calculate delta Hn? No, because the mole here is the same thing as the mole here. We set it that way because this is where the reaction is end point, right? It is 0.0125 mole. Because as you can see, I can multiply these two or multiply these two, and they both will be 0.0125 mole. So to finish this question, to just call it delta Hn is equal to negative 1290 joules divided by 0.0125 mole. So my answer, of course, is joules per mole. 103,200 joules per mole. Again, don't forget the negative sign because it's just that important. Okay. So what this means is this. So that's a way to explain what's going on. Is very simple. So you put 0.5 molar at 25 milliliters of acid in there. Okay. Then you're going to put 0.8 molar and 0.0156 liters of base in here. Now, you might have not put all of these base in there. You might do a little titration and just let it drip, 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 drip in there until the 2 volume or the 2 moles would equal. Okay, and due to MC delta T, knowing the fact that the 2 volume is equivalent to the mass right here, use water because these are of course water based. And note the temperature being 7.6. What that means is that the temperature change when these guys react, well, it's going to be 7.6 and it's going to be exothermic. Okay, and you're going to get negative 1,290 joules. That means negative 1,290 joules of energy got released out to the surroundings. To figure out what's the molar enthalpy, you just divide the mole of this. Or that. It's really the same number. All right. This is actually a very interesting question. It's a very interesting lab, actually. That's one thing we're going to do, okay? In a couple of days, we're going to do titrations. That's right. You may be thinking, I already did titration. At least I've seen it done. We're going to do it a little differently. We're going to do titration a little differently. We're not going to put in the indicator. No indicator this time. Instead, we're going to put a temperature probe. And you'll see that you can actually still do titration and you can still get a very accurate result. In fact, it is even more accurate when you do titration this way. The reason why I said it's more accurate is because, hey, remember that annoying part where you have the final drop to get the endpoint? And if you miss that final drop, yikes. It doesn't matter in this case. You are going to continue and continue. This time, you're gauging not through color change, but gauging through a drop in temperature. Yeah. Anyway, let's call it for today. Those are the 3 types of questions that for sure you're somewhere down the road that you're going to encounter. So make sure you know how to do these things. All right. Bye, guys.